I had a question. Obviously, being a theoretical physicist, use a lot of mathematics to help understand this concept and organize these models that help explain the universe.
Yes.
I want to know from the bottom up is how a mathematical formula is postulated, how it's come up with, and how that leads to eventually going to CERN and going, okay, we can test this. I know it's a very broad question.
It's a very interesting question. There's no way to give a simple answer. I mean, the basic fact is that mathematics has proven to be the best way by far to precisely understand the fundamental laws of physics and hence of the universe. Why that is the case is a mystery. I think it was something that Einstein, for example, was rather taken by. He knew, he was a master of using mathematics to understand the universe, but why it was that worked, he found mysterious.
So would you find that generally you would have a theory, have an idea, and then try to apply the maths to prove this theory, or does it sometimes work the other way around, in which you'll be experimenting with different mathematical models, which in turn answers your question?
So
offers answers that you weren't even looking for, I suppose.
Congratulations, that's a very interesting question. So it can go both ways. So typically, so it can be that you are imagining some new way of understanding a physical system in your head. You're just imagining it. And you're not thinking of it in terms of solving equations, but you're just imagining things about it.
Even it's to actually visualize it?
Yeah, it can be visualization. It can be all sorts of things. That would be an interesting topic to discuss in its own right. Not sure I'm the most qualified, but there's a creative. One thing I like to get across about science is it's a strongly creative activity. I don't know. One of the things that irks me, I guess, about the way that the general public sometimes think about science and scientists, and this is maybe comes across a little bit in popular culture, is that somehow we're very dry individuals who you just collect a lot of data and then we work out the truth.
Yeah.
And in fact, it's not like that. I mean, we do collect a lot of data and we do work out the truth, but there's a lot of creativity and imagination that has to go into it, and sometimes there are just blinding flashes of insight that come from nowhere, right?
Yeah.
Which are imaginative leaps, and then you about the way certain physical system or whatever it is you're studying, may actually operate. And then what you do is you take that intuition and you make it precise.
Yeah.
Right. And making it precise in physics means putting it in mathematical form. And then you can work out in great detail what's going on, not just qualitatively or heuristically, but in full quantitative detail. And then you can compare with experiment and see whether your hunch about the way things work is really true. I mean, this is what Einstein did when he invented the theory of general relativity, which is his theory of gravitation, actually. He had a vision for the nature of gravity based on just one of the most basic things that had been observed about gravity. And he built on that over a period of several years, and eventually constructed this elaborate mathematical theory, general relativity, and it predicted some when you looked at the equations, when you actually solved the equations, right, which is now a very precise thing. He first of all could explain a famous anomaly about the orbit of Mercury around the Sun that had been a mystery for some time, and it turned out that his equations completely explained the behavior of Mercury, whereas Newton's law of gravity didn't. So that was an important thing for the theory, but also he predicted new things. He predicted that light would be bent by large masses. So light is bent when if a light beam is passing a star, it gets bent in the gravitational field of the star. So this is a famous prediction of his theory that turned out to be correct. all sorts of things now about gravity that were first known about through solving his equations turn out to be correct. For example, the GPS system that everybody uses now to work out how to get to the supermarket or whatever, that system relies on general relativity in order to work properly, because clocks tick at different rates depending on the strength of the gravitational field, and you have to take that into account. So there you go. It's a process of looking at what the world looks like, then appreciating what you don't understand, and then having some insight about it.
And I suppose mathematics is just an awesome tool.
And then the
for
mathematics,
testing your
mathematics becomes a tool eventually, and you don't really have a physical theory until you've put it in mathematical form, right? At least that's the way it is at the moment. Now, you also asked about the process going the other way.
Yeah.
Sometimes are you just playing around with mathematics, and then you find it has a physical application. Well, that can happen too. I would guess it's rarer than going from physics to the mathematics, but it has happened. So, for example, a famous physicist called Paul Dirac, one of the founders of quantum mechanics, he invented something called the Dirac equation, and he was sort of fooling around with mathematics when he did that, and he advocated this approach. What you should do is, he said, play around with elegant mathematical formalisms, and maybe they'll have some relevance to the real world, and sometimes they do, and sometimes they don't.
Maths doesn't lie, though, so it's always a good place to start, right?
Well, it can be a place to start, but I guess you can start wasting your time if what your aim is to do is to explain the real world. You might say, oh, I really love this mathematical structure, let me play with it and see if it has some relevance, for nature. That may be taking a bit of a risk from the point of view of wasting your time, because it may be a nice mathematical object, but doesn't actually help with physics. So there are certainly examples of that. So the interplay between physics and mathematics is very much a two-way street. It goes backwards and forwards.
Mutually supportive.
Mutually supportive. That's right.